Hello, my name is Mingwan. Today I'm going to talk about the data-driven method for computing a polyhedral invariant set of black box switch linear system. This is joint work with Rafael Jungers. So this is the outline of my presentation. First, I'm going to talk about the definition of invariant set and model-based method for computing invariant set. Then I will talk about the proposed data-driven method for computing invariant set. So in this talk, we are interested in switch linear systems, which are systems that are switching among a finite set of dynamic models. Here, an important concept is called the joint spectral radius, which is used to describe the stability of such a system. So if the joint spectral radius is less than 1, then the system is asymptotically stable for any switching sequence. Here, we would like to make a few assumptions. The switching signal is not known, the dynamics are not known, the joint spectral radius is less than 1. So when the switching system is not known, then it is proved that the identification of the switch linear system is NP-hard. Here is the definition of invariant set. A set is called the invariant. If for any point inside the set and for any mode, the next state remains in the set. For convenience, we would like to define the concept called C polytope. Polytope is called C polytope if it is convex and contain the origin in its interior. With the polytope, we can also define the Minkowski functional as this, which is also a set induced distance. This will be unknown when the set is symmetric and contain origin in its interior. So with these definitions, here we have two properties. As C polytope S is an invariant set if and only if this inequality holds for any x inside the unit sphere and for all the switching modes. The second property says when the spectral radius is less than 1, there always exists invariant C polytope. So these are the model-based method for computing invariant set. We have method based on linear programming, based on linear LMI, based on SOS. And for complicated systems, we also have an abstraction-based method. And these are a few toolboxes for computing invariant set. Now I would like to talk about the proposed data-driven method for computing invariant set. So first we need a set of data. So we sampled the data, we sampled the initial state and the models, and this is the sampled data. Then we observe the trajectories. So this is the initial state, and this is the next state. So here we don't have to know the switching mode, switching signal. All we have to know to observe is the next state. Then with this sample data, we aim to find C polytope such that this inequality is satisfied. Then if we parameterize the set with the matrix F, then the problem will become a parameterized problem as this. But here, because we don't know the size of the matrix F, and this is this constraint is difference of two convex functions. So it's not easy to compute this to solve this problem. So instead, we use the fixed point iteration. There are basically two types of fixed point iteration here. The first one is called the backward fixed point iteration, which is the one step backward reachable set. And with this, then this iteration will converge to largest invariant set contained in X infinite time step. The second one is called the forward fixed point iteration, which is the one step forward reachable set. And this iteration also converge to the smallest invariant set that contains X infinite time step. But as we found out, it is easier to adapt the forward fixed point iteration in data-driven computation. So here we use the forward fixed point iteration. All we have to do is to replace the one step forward reachable set with the propagation of the sampled points. Then, because we only have a finite number of points, the computed set is always a subset of the actual set, and the sequence is also convergent, but not necessarily infinite time. And finally, it will converge to a feasible solution to this constraint. So here we show that if we keep increase the number of points, then the computed set will converge to the actual set. But the question is, if we only have a finite number of points, is the computed set invariant? To answer this question, we will derive two certificates. So the first certificate is from the scenario approach from campaign in 2018. So here, this V is basically the set of points that violate these constraints. We call these bad points. So here it basically is basically the measure of the bad points, and this S is the number of supporting points, which are basically the bounding points that cannot be removed from the constraint. So for formal definition, we would refer to this to campaign's paper, and this function is defined based on beta. So this says the measure of the bad points greater than this epsilon with with probability no larger than beta. So then with this chance constraint theory, we would like to discuss the concept called almost invariant set. So the definition is given here. A set is called the epsilon almost invariant if the measure of the good point is greater than 1 minus epsilon, or in other words, if the measure of the bad points is less than epsilon. So this mu here is the uniform Sheffield cap. Then with the chance constraint theorem, we get our first certificate with probability no smaller than 1 minus beta. The computed set is almost invariant with the epsilon being this. So to derive the second certificate, we need the concept of a lambda contractive set. The definition is a standard. Here we just have to take all the dynamic models into consideration. Then with this definition, we can see the set is when the set is epsilon almost, we can always computing a contraction rate, which means the set is always lambda contractive. Then the rate is basically defined by this gamma function depends on S and the epsilon. But for computing the exact value of the gamma mean function, it's very difficult. So in practice, we just compute a low bound of this. Then we also need the concept of covering and packing number. So again, the definition is a standard. We only adapt the definition to the union sphere, and we call this the NC, the minimum cardinality of epsilon covering. And then the NP is the maximum cardinality of epsilon packing. Then here we can get inequality. And this complicated term arises from the relation between the angle and the measure of Sheffield cap. So the details given here. So when the measure of the Sheffield cap is epsilon, then the angle is theta epsilon. So derived from this regularized incompleted beta function. Then with this, we get our second certificate. So for any epsilon with probability no smaller than 1 minus beta, defined here, this computed set is lambda contractive with the contractive rate being this. Then we have two certificates we would like to make comparison. We fix the confidence level to 0.001. Then we computing the contraction rate from the first certificate, which is denoted as the lambda epsilon. And for the second certificate, we let the lambda beta being the contraction rate. As we can see, the dashed line is the contraction rate of the first certificate, and the solid line is the contraction rate of the second certificate. So it's obvious that the second certificate is better in terms of contraction rate, but this is a bit unfair because in the first certificate, we also have the measure of violating subset. So with the contraction rate, we can also approximate the GSR because of this homogeneous property. So all we have to do is to find the minimal scaling such that the scale the data with the scale data, the iteration converge. So then with the theory with the result above, we can see with probably no smaller than 1 month beta. This will be upper bound for the joint spectral radius. Then to conclude, we extended the fixed point iteration to switch the black box switch linear system. To derive probabilistic guarantees, we use the concept of almost invariant set and the lambda contractive set. With the contraction rate, it is also possible to approximate spectral radius. Thanks for listening. That's all for my presentation. Now I will be very happy to take any questions.